Now that we have a clean DSM clipped to building footprints, we can start extracting geometric features, slope, azimuth and surface roughness. This will help us understand how rooftops are oriented and whether they are suitable for solar panels. We begin with slope and aspect, which we can compute using QGIS terrain analysis tool or with the GDAL library. Both derive this information directly from the elevation raster. The slope tells us how tilted each part of the roof is, usually expressed in degrees. A flat roof has a slope close to 0, while steep roofs reach higher values. The aspect or azimuth indicates the direction each surface is facing. This is key for solar PV, since south-facing surfaces receive more solar energy in the northern hemisphere. But raw aspect values range from 0 to 316 degrees aren't always intuitive. That's why we reclassify them into 4 main cardinal classes: north, east, south, and west. For example, surfaces between 135 and 225 degrees are considered south-facing. This classification can be done with the raster calculator or in Python. But one important note here. Always pay attention to the azimuth convention. Some systems, like PVGs, define south at 0 degree. This can lead to confusion or incorrect orientation classes if not handled carefully. Now, let's talk about roughness. This measures how irregular the surface is and helps us identify small obstacles like chimneys, railings, or equipment that might interfere with panel installation. In QGIS, roughness is calculated using the Terrain Roughness Index tool. The result is a new raster where higher values indicate bumpier surfaces. To clean up the roof surface, we can apply a threshold, for example, masking out all pixels where roughness exceeds 1.5 times the average value. This leaves us with smoother, obstacle-free zones. This method is fast and works well with high-resolution data. But it is important to remember that the choice of threshold is somewhat empirical and may need to be tuned for different contexts. There are also alternative methods for filtering roughness. For example, you can compute a local mean in a sliding window and remove values that deviate too much from that local context. This helps adapt the filter to gradual slopes. Another option is a morphological filter, where the roof surface is eroded to find a base level and deviations from this base are treated as obstacles. This works particularly well for flat or industrial roofs with isolated protrusions. Finally, we can compute zonal statistics. For each orientation class, we calculate the available area and the average slope over all buildings. This gives us a directional breakdown of usable surface, which is extremely useful when planning solar installations. South-facing areas with moderate slope and low roughness are generally the most efficient. These statistics can be exported to CSV and used in solar models, or visualized directly in QGIS. So, in summary, we have derived the 3 key parameters that define rooftop quality: slope, orientation, and surface regularity, and we have aggregated them into usable statistics. In the next video, we will automate this entire process using QGIS graphical modeler, so it can be applied to any city with minimal manual work.